Okay, good morning. So, we finished this last part of this chapter, exponential form of complex numbers. Okay, so let me just review. So when we started talking about complex numbers, every complex number z is a number that can be written in this form, in which a and b are real numbers, and I is the square root of minus 1. Okay, so that's called the standard form or Cartesian form. Okay, and then we introduced the notion of the complex plane, which was essentially the same as the normal plane, but we relabeled them with RE for real and IM for imaginary. Then we could represent every complex point on the complex plane as a point or as a vector. As a point, so this is the real part, this is the imaginary part. So I will actually get this one. Let me see if I can turn on. There is no light here. Okay, so this point we call it z, and then we also learned that we can represent it by a vector, which is from the origin to the point, and then we learned the length of this vector is the absolute value, so usually denoted by that or this symbol, and this is exactly equal to a square root of a squared plus b squared. And then we also learned that this vector makes an angle with the positive real part, with the positive part of the real axis, and then I have this theta, and theta is called the argument of z. And now when we have these two clear, we can write the polar form of the complex number. So the polar form looks like this, yes? Z equals to, you take that number r, put it here, and then you have cosine theta. Theta is that argument plus I sine theta. And this is called the polar form, yes? Okay, so and we learned why we want to go through this trouble. Are you coming? So, so what was the reason? Do you remember? What was the reason we go through this suffering to go from the Cartesian part, which is simpler, to this one? Yes?
To calculate out higher powers.
Higher powers, because it turns out we were able to show that if we put the number in the polar form, if I want to raise this to the power of n, this number simply goes to power n, which is not surprising. In principle, I should put a power of n there, but it turns out that if this has this particular form, if you put n there, it will be equivalent to multiply n by your angle. So that was the reason actually we did that. Okay? So this is the reason why we do that. So now today we want to talk about another form which is actually very important, and everything seems natural. This is a little bit artificial, so I mean that in principle you need to know the rule. If you have forgotten that one, it is probably not that easy immediately understand that this is the connection. But if I teach you this one, exponential form, then you see that this becomes very natural. Okay, so that's why it's good to know about that one, and that's the last part of this chapter. Okay, so this is a little bit a strange formula. We want to, I don't want to prove it for you, I just want to motivate why we should expect this. So I would say that let x be a real number, x be a real number, then e to power ix, e is the Euler number, ix equals to cosine of x plus I sine of x. It's a very, very important formula, and that's called the Euler's formula, yes? Okay, so I emphasize that x is a real, and I want to calculate cosine x and sine x, so it means that x is expressed in radians. So this formula only is working if x is expressed in radians, okay? Of course, if x is not in radians, you still can calculate the right-hand side. For example, if I choose x to be 30 degrees, cosine of 30 degrees is a number, sine of 30 degrees is a number, you put that number, you get that one. But then it is not equal to e to the power of I times 30 degrees. So if you want to have this equality valid, an x has to be a real number, dimensionless number expressed in radians. So let me emphasize on the word real. This formula is not valid if x is not real. Okay? But it's a very, very important formula. The only thing, I will follow the book to motivate you why you might expect this formula is correct. That's not the proof, okay? Yes?
I don't know if I'm skipping forward, but is this related to that that e to the I pi is equal plus 1 is equal?
Yeah, yeah.
Is it that?
So some people say that's the most beautiful formula in whole mathematics.
So
Yeah, we'll come back to that. Yeah.
Okay, okay.
Yeah. So now let us try to motivate. So motivation, yes, not proof. Okay, so what we do, I would say that I introduce a function. Let f of x be equal to cosine x plus I sine x. That's a function that I introduce. And I assume that what we learned about the derivative of real functions also works for the derivative of complex functions. Of course, this is not something extra. Do you remember when we started the lesson of complex numbers, our motivation is that we add one rule to the game, and then we want to keep everything more or less as we had before. So it is not something very strange that if we demand that the derivative of sine and cosine still is working, the rules of differentiation works. So I introduce the right-hand side of this expression as a function, and then I differentiate it, okay? Then, it might seem a little bit strange, but you have to be patient to see why. Why it is a good motivation. So then I take the derivative. So you know the derivative of cosine x is minus sine x, and that is the reason that x has to be expressed in radians. You remember the formula, the derivative of cosine becomes negative sine is only valid if x is expressed in radians. And then I have plus I cosine x. I is a constant. I'm assuming it's a constant, so I don't take the derivative of I, so I just take the derivative of sine x. But now the trick is to factor an I out, so this becomes I. Of course, there is no I here. I will write it as minus 1 over I, and then sine x, and then I have plus cosine x, yes? So if you want to convince yourself that what I have done is right, you multiply back. If you multiply I back here, this I and that I are cancelled, minus 1 is left, minus 1 times sine x is minus sine x, and I multiplied by cosine x is exactly that. But now I don't know how many of you remember. So do you remember what can I write for 1 over I? If you have forgotten, let us just do
It's
that.
minus.
Yeah, it's minus I, so it becomes positive I. Let us redo it here again. So I rescale this by I. So I have done nothing. I just multiplied by 1. Okay? But then minus 1 times I, it goes to the numerator, and I times I, which is I squared, goes to the denominator. But we know what is I squared. I squared is minus 1, so this becomes simply I. So this expression that you see here is just simply I. And then let me just again change them in the normal order. So I write cosine first, I sine x second, but of course I have an extra I factor of I there. So this becomes I, and then so let me write it once more. Cosine x plus I sine x. Yes? But this is what again? The combination that appears here is exactly the same as f of x. So what happens now? Then it means that the derivative of this function, whatever this function is I times the function itself. Yes? So we got this one. But you have enough experience of this one. If this I was not there, I hope that you can immediately guess your function, the type of, e to the x, yes? If the I is not there, you ask yourself, what is the function whose derivative is equal to itself? And that's the famous e to the power of x function. But now you have I here. It's not hard to, by the way, e to the power of x is not the only function whose the derivative is equal to itself. What is another function, for example? It cannot differ that much from e to power x, but what I'm saying is that you can tell me another function whose derivative is equal to itself. Yeah, just say it, yeah.
X equal to 0.
What?
If it's just equal to 0, then its derivative is also...
No, so give me another function. So Aaron told me this function. That's correct. The derivative of this function is equal to itself. But can you tell me another function whose derivative is equal to itself? It shouldn't be hard.
E to the power x plus 1.
Plus 1, yes. Why are you hesitating, yes? E to the power of x plus 1. Plus 1. The derivative of this one is also e to power x. So there are infinitely many functions whose derivative are equal. This is not equal to itself.
Yeah.
Yes, it should be equal to itself. Yeah, because what you said is not.
No, I meant e to the power x plus 1.
Yes, that's correct. That's what I was wrote in that way first. Okay, so you mean this one, yes? Yes, that's correct. The derivative of this function, according to the chain rule, e to the power something, it becomes e to the power of x plus 1, but it is not finished. You have to multiply by the derivative of the numerator, the exponent, but the derivative of this one is 1, so it is correct. That's also another function, yes? So you see that e to the power of x plus c, any c, if I take the derivative of that, it becomes e to the power of x plus c. Okay, now if I ask you to give me a function, whose derivative is not equal to itself, it is 2 times larger than itself. For example, can you give me a function h whose derivative is not exactly equal to itself, but it is 2 times larger than itself? It's not also hard to find. Yes?
E to the power
2x. Yes? So for example, e to the power of 2x, because if I ask you to differentiate that, you know that the function repeats itself, but you have to multiply by the derivative of the exponent, which is 2. Okay, so now this is similar to this situation. I want you to guess a function whose derivative is not exactly equal to itself. It is I times, of course, larger. That's not a good word. Yes? I times the function. What is that function you guess?
e to the ix.
E to the power of ix. Okay? So this is what we guess. But is it the only option that we have in hand?
No.
No, because of this idea that you told. So I can add a constant to it, yes? So this is not the only option. So we can conclude that, and then I can write for some constant, it is important, constant c. So far, what I have shown, I started from f of x this, and I was able to convince you somehow, hopefully I was successful to do that f of x is also equal to this one. So if I compare them, it means that this expression for some still unknown c is equal to that expression. Yes? The problem is that what that c is. My claim is that c should be 0. Okay? If I can prove that c is 0, then I am done. I have this equality. Okay? Is that clear? So how can I prove that c is 0? So let me write here so far. So therefore, for some constant c, we have Of course, let me put a question mark. Still, we don't know that which c is that. We have what? We have this expression, which is f of x, is equal to this expression, which is also equal to f of x. So I have proven so far that I have this. But that's not exactly what I want to prove. I want to somehow get rid of that c. But how can I get rid of that c? You remember, I emphasize that c is a constant. Yes? So how can I get rid of that c? Or how can I determine what c is? Remember, c is a constant. I'm emphasizing. What is the meaning of that? No ideas? So let me choose a number that I can calculate, yes? So for example, I would say let this formula is valid for all x. But the problem is that I don't know for which choice of c. To determine that c, I would say that because this is valid for all x, I would say that this is valid for all x, including x equals to 0. Yes? You could choose the other numbers. The reason that I choose 0 is become clear. So then I replace x with 0. Okay, let me stop again. So do you agree that from here I can go here or not? Because this is a formula valid for all choices of x. So if I choose x anything, the left hand side should match with the right hand side. I decide to choose x to be 0, so that is also valid. Okay, why? It is good because I times 0 is just simply 0. 0 plus c is c, so I get e to power c. And on the right hand side, cosine of 0 is 1. Yes, and the sine of 0 is 0. So what do I get? I get e to power c is 1. Okay, so what is c then? 0. Okay, so this means that c is indeed 0. So I told you this is not a real mathematical proof. There are some ambiguities there, but that's a good motivation why we think that this is a good formula. So what we want to write is this. So I would write that x belongs to real numbers. This is extremely important. Then Euler's formula tells you that e to the power of ix is equal to cosine x plus I sine x. Okay, so let me emphasize x on the right, so x on the left. Because on the right it doesn't matter. So let me write. For this formula to work, x should be expressed in radians. Okay, so this is what is called the Euler's formula. So now, as what Rocco mentioned, let us calculate e to the power of I times pi. Okay, so you compare this one with this one. Is the Euler formula applicable here? Yes, because that's exactly of that form, but more importantly, this one, which is pi, is real. So then you can use this formula. So what can I write? I can write cosine of pi, so I give the role, this is my x in this problem. And this is good, because this x is a real number. So this becomes cosine of pi plus I sine pi. But if you know from your lessons, cosine of pi is -1, sine of pi is 0. So if you calculate that, e to the power of I pi becomes -1. Yeah, some people write it in that way, but I prefer to bring it to the left and write it like this, yes? So you see, this, by many people, this is called the most beautiful equation in mathematics. Because first of all, it is very simple, and it is, of course, elegant. Why? Because there are 4 fundamental constants in mathematics. 0 is the additive identity, 1 is the multiplicative identity, I is the imaginary unit, pi is the famous pi number, and E is the Euler number. So you have all those constants in one simple, elegant equation. So from now on, so you see that this is valid. So e to the power of I pi plus 1 is 0, or some people write it like that. Okay. For example, let me ask you to calculate this. For example, e to the power of minus I pi over 4. My question for you is to calculate, so let me write this example. Example, let the complex number z be like this. Determine, for example, the real part of z, the imaginary part of z, and the absolute value of z. We want to determine these 3 numbers. Remember this, whenever you are supposed to answer these 3 questions, real, imaginary, and complex absolute value, you have to have the standard form. Okay? So you have to change your complex number into the standard form and read it. So if I am able to change it like this, then answering these 3 questions become very simple. This part I pick up for the real part, the coefficient of I, not the whole expression. The coefficient of I pick for imaginary part, and then I will square root of a squared plus b squared. This will be the answer to this. So whenever you are supposed to answer these 3 questions, remember, you need to put your complex number into the standard form. If it is already standard form, that's good. If not, you have to change it. Okay? So then you know that, is this formula applicable here?
Yes.
Yes. But the problem is that I should have a positive sign here. I have a negative sign here, but that's a small change. Yes? I move this minus sign to pi over 4. Yes? So the first thing that I will do is that z is equal to e. Instead of writing negative I write it positive I, and I multiply the minus sign in. First of all, I haven't done any changes. This is exactly the same thing here. But now, what is the benefit of that? Because now it is exactly according to Euler's formula, so I can give the role of my x to this guy. And then, of course, use the formula. So this becomes cosine of negative pi over 4 plus I sine negative pi over 4, yes? Okay, but I hope that you remember from trigonometry lesson, chapter 2, that cosine, if I have a negative sign in front of a cosine, what will happen?
It disappears.
Disappears. And then here, it goes out. So it becomes cosine pi over 4 minus I sine pi over 4. But this is a famous number. Of course, if you don't have it in your memory, you can just look it up. And if this is not a famous angle, probably you will have able to use your calculator. But this is a famous number. Cosine of pi over 4 is 1 over square root of 2. Sine of pi over 4 is coincidentally the same. So this becomes 1 over square root of 2, but I have an extra I here. So if someone tells you this, that's exactly the same complex number. And now if I ask you what is the real part of z, you can immediately answer it's 1 over square root of 2. What is the imaginary part of z is minus 1 over square root of 2. And by the way, what is the absolute value? It is the square root of the real part to power 2, which is 1 over 2, plus the imaginary part to power 2, which is again 1 over 2. So it becomes 1. Square root of 1 is simply 1. So this means that the absolute value of z is 1. Okay? By the way, the absolute value of this number is always 1, regardless of x. Can you see that? Can you see that why? Because if I ask you to calculate, let x be real. If I ask you what is e to the power of ix absolute value, you always, if you want to answer these three questions, you have to have the standard form. But the standard form we know, we have to use this. This is the standard form of this number. This number is the real part, this number is the imaginary part. So what you do, first you put this in the form of standard form, and then this becomes a square root of the real part squared plus the imaginary part squared, yes? But this is a famous formula. It's always 1 regardless of what value you choose for x. So that's why it was not surprising. If I change pi over 4 to even a very strange number, for example, if I choose, if I ask you what is the absolute value of e to the power of I don't know, for example, times 0.705. I'm expressing it. So what's the answer? This should be expressed in radians, of course, but the answer is
1.
Yes? So you remember, this form, the absolute value of this form is 1. Okay, so now let us go back and talk about the exponential form, because assume that someone told you the polar form of your complex number. So the polar form of your complex number is a non-negative real number multiplied by cosine theta plus I sine theta. So theta is a real number. That's the polar form. But now we learned by Euler formula, I can write this as e to the power of I theta. Yes? And then everything becomes very compact and very nice to work with. Yeah? So z becomes suddenly r e to the power of I theta. This is what we call the title of the lesson. So the exponential form of z. So if I ask you to put a number, a complex number in the exponential form, the method is the same. You have to know r, you have to know theta. But instead of putting it in this formula, you put it in this more compact formula, then it becomes the exponential form. Yeah, so that is not hard. For example, let us just do a simple thing. So let z be equal to 1 plus I. Determine, let me make it a little bit more interesting. So let us put a minus sign here. So determine the exponential form of z. So you see that the exponential form for this one, I need r, which is absolute value. I need theta, which is the argument. So again, the first parts are exactly the same as if you want to put it in the polar form, yes? So what I need to calculate, first I need to calculate r. So what is r? R is the absolute value of my complex number, which by the formula is the real part squared. Okay, what's the imaginary part?
1.
1. Don't say I, yes? The imaginary part is 1. The coefficient of I is the imaginary part. So this becomes square root of 1 plus 1, which is 2. Square root of 2. But I need to determine theta. But to determine theta, I told you it's better to sketch something for yourself. So this is the real axis and this is the imaginary axis. So the real part of my complex number is minus 1. So let us say it's minus 1. And the real part is 1. So this is I actually. So this becomes that point. And the vector is from here to here. But the angle that you are supposed to write is this angle. But what is that angle? because you know what is this length? This length is 1 unit. What is that length? It's also 1 unit. So this is a right angle triangle. It's also an isosceles triangle. So this angle and that angle should be 45. Yes? But I want to know theta. So theta is 180 minus 45, which is 135. In the case of, be careful, in the case of polar form, you can use degree and put in degree form. But if you insist to write it in the exponential form, this is a have to. You have to change to radian mode. Okay? So in the polar form, if you are not forced to do it in radian, that's up to you. You can put degree here, 135 degrees, 135 degrees. But if you want to write it in exponential form, this is a have to. So what is theta then? In radians, the full angle, which is pi, which is 180. In radian, it's pi. Minus that angle 45 in radian, it becomes pi over 4. And if you simplify that, it becomes 3 pi over 4. Okay? And now everything is ready. So what you do, you just have it in the formula sheet. So z becomes r, which is already calculated, e to the power of I, 3 pi over 4. So this is the answer to this question. Okay? So by now, why this is good, do you remember I told you that the reason that we go and make this trouble for ourselves to put this in the polar form is because if I want to raise it to high powers, it becomes simple. So this becomes r to the n cosine theta plus I sine theta, okay, to the power of n, but we learned that this n, so you need a teacher or you need to study yourself to understand that this n goes inside like this. It is not trivial, yes? You will be in video, okay? Yes, that's okay. That's why we publish it, okay?
That's fine.
Yes,
What can I do?
Thank you. Yes. Okay, so cosine n theta plus I. Okay, this is a little bit. So I mean, the step from here to here is not trivial. So you have to convince yourself, and you remember the discussion with Hussein last time, yes? So it was not trivial. It shows that. But now, if I want to write my complex number in that one, it's automatically clear. Yes, that's the benefit of working with exponential forms rather than working with polar forms. Okay, because if you work with the exponential form, you will have all the benefits of the polar form, but you don't need to memorize anything. For example, if I give you this number, and I ask you to raise it to power n. Even math 1c lesson is probably enough. You just say that this is the product of these two. I want to raise it to power n. So what do? You raise this part to power n, and then you raise the second part to power n. But you don't need a new teacher to tell you that how to do that. What do you do here?
Multiply.
You just multiply. Yes? So this becomes r to the n, e to the power of I n theta. So this multiplication by n becomes very natural in this language. So you have all the benefits of the polar form, but in a more natural language. So for example, so I can, for example, give you, let us work with that number. Of course, let me raise this number let me ask you in the previous example, this one. Let us calculate z to the power of, say, 100. Okay, so we want to calculate. Of course, you could do it using the polar form, but it is more natural to do it with the exponential form. So you calculate the exponential form, okay, and then you put it here. So the question mark becomes, the exponential form is this number, e to the power of I 3 pi over 4, and then I raise it to power 100. So you know that this number to power 100, what's the answer? Because square root of, square root of 2 is 2 to the power of 1/2. So when I raise it to power 100, I have to raise this to power 100. But this becomes 2 to power 50. But then you don't need to remember anything because it's extremely natural. So you need to raise this to power 100. But how do you raise an exponential to another power? You just multiply the exponent. So what happens? And you do it in your head. You multiply 100 by 3 pi over 4.
150.
100, yes. Yeah, 104 are simplified. It becomes 25, and 25 times 3 is 75. Yes? So if you want, I can write it like this. So it is done. But usually, when they ask you to calculate high powers, they expect you to write it in a standard form. Okay, so we have to use the Euler's formula to switch back to the standard form. So you see, it was already in the standard form. Because I wanted to calculate high powers, I have two choices now, either to go to polar form or go to the exponential form. I chose the latter one. I raise it to power 100, I got it, then I go back to the standard form again. But going back to the standard form, 2 to the power 50 is a big number, so that's it. And then I use the Euler's formula. I hope that you have it in memory. This is going to play the role of x. So this becomes cosine x 75 pi plus I sine 75 pi, yes? And then 75 pi, where is it on the unit circle? Multiples of pi are either here or there, but which one is that for this? 0 pi is here, 1 pi is there, 2 pi is here, 3 pi is there, 4 pi is there. So it means even pi's are here, odd pi's are there. So 75 pi is exactly here. But you know what is the cosine? Cosine is the x-coordinate. What is the x-coordinate of that point? -1. What is the sine coordinate? 0. So this number is just simply -1, and I multiply it there. So the answer becomes -2 to the power of 50. Yes? So this means that this number raised to power 100 turns out to be a real number, a negative number. It's also strange, yes? Why this is a strange? A little bit strange if you have your intuition from real numbers.
Maybe.
Raise it to an even power.
Yeah,
but
it
it's
shouldn't be
negative.
negative, but it turns out to be negative, yes? Of course, you know that in complex number, weird things can happen, and that's the fun, by the way. Okay. By the way, this has a very simpler way. So I mean, in the exam, if I want to do it, don't suffer to do that. So I would do that. I will first calculate z squared. This is exceptional. I just realized that, okay? Because if I want to ask you, can you raise it to power 2? What's the answer? It was an exception that we can do it, okay? Like this. The first one squared is 1. 2 times the first one times the second one. The second one squared is I squared. Because I squared is accidentally -1, I can solve it easier. So this is just -2i. But my goal is to calculate z to the 100th, so this becomes z to the power of 2 to the power of 50. But z to the power of 2 is -2i to the power of 50, so it's -2 to the power of 50, I to the power of 50. But that's very strange, this is not working. Is it? What is I to power 50? Is it -1? Yes, it is. It's -1. Yeah, it's working. Because -2 to power 50 becomes +2 to power 50. But I to the power of 50, I can write it I squared to the power of 25. But I squared is what? -1. -1 to the power of odd becomes -1. Multiply this one, I go back to negative again. That's also possible. But this, I just want you to know, that was a coincidence that this method works for this particular case, because when I raise it to power 2, this one and that one are cancelled. If this number is not -1, is for example 2, then this will not work, okay? So that was an exception. Okay, so that's it. This is the lesson. But let us try to solve some problems from the book. Okay, this is not the lesson, sorry. Because there is one natural question. What is that question now? So let me write the Euler's formula, it might help you. So this was the Euler formula, but there was a constraint. I was not allowed to use the Euler's formula unless
You need it to be a real number.
yes, x is a real number. Okay, is that the natural question? We are working in the set of complex number. The natural question is that what happens if x is not real and it's a complex number? Yes? So we want to answer that. Let us see what happens for this guy. Z is a complex number. Might be this is a little bit beyond the scope of this lesson, but okay. So let me ask you something else. So what do you think if I raise e to power say 1 plus pi over 4i? And if I didn't give you this 1 here, you know what to do. That's exactly the Euler's formula. But do you think that if I put a 1 here, you cannot solve it? How can we solve it? For example, let me ask you, what is the real part of this number? So how should I solve that problem? This is not exactly according to the Euler's formula. What should I do here?
Can you write that e times
Yeah,
e to
exactly.
power-
So why you hesitate to say? So e to the power of this one can be written as e to power 1 multiplied by e to the power of 4 pi over I. So let me write I on the other side. Do you agree? And then this one is just, it's not a mysterious thing. 1 is real, e is real, so e to the power of e is just a normal e. But this one is a little bit strange, that we learn what to do with that. So this becomes what? Cosine pi over 4 plus I sine pi over 4. Yes, and then what happens? Cosine pi over 4 is 1 square root of 2 and plus again the same number. And I multiply that, now this becomes my standard form. So I was because whenever you want to answer the real, imaginary, and the absolute value, you have to have the standard form. So the first thing that came to my mind is to put it in the standard form. I did it using what Gustav mentioned, and now I want to find the real part. So what's the question mark here? This is the real part, yes? Okay, so let me skip this one because this becomes a little bit this turns out to be interesting. This turns out to be that this is the Euler formula is also valid. So if you want to have a general knowledge, this becomes cosine z plus I sine z. But then what is the question? If I just write that, I say that, okay, accept this is working. Are you happy?
No.
Why not?
What?
You have an imaginary number and cosine is
Exactly, it is strange, but there is a meaning for that. Okay, so that's exactly. But it turns out it's not in the book. So e to the power of I z is cosine z plus I sine z. Then the question is that if I ask you what is sine of 1 plus I, what is the meaning of that? Yeah, what is the meaning of sine plus 1i? And a strange thing can happen. So complex sine and cosine can also be larger than 1. So very weird things can happen, okay? But that's not part of your lesson, so let us skip that, okay? But if you want, yeah, it's good to know what is the way. Of course, if you want, this is not so mysterious. I can define it. It's not very hard. But before doing that, I want you to answer this question. So, what is, if I give you e to power x plus yi, and then I say x is real, y is also real. So I am answering this question. I am answering e to power z. I want you to tell me how should I interpret a complex exponential function, okay? So z is equal to x plus iy. This is not hard. This is, you can immediately do that. Yes. So I want you to rely on your intuition. That is the definition. I want to continue. So some person comes to you and say that, okay, Babak, if you say e to power 5, I understand what does it mean. But if you say e to the power of 5i, I didn't understand about it, but after learning about the Euler's formula, I still do understand it. But if you tell me what is e to the power of any complex number, say 5 plus 5i, then I still want to understand this one, but that is what you mentioned here. So if I give you any complex number, e to the power of that complex number is known to you, yes? It's the definition. So e to the power of z is this one, but how can I understand that? I can decompose it in my head, as Gustav mentioned for that example. This one, it's not mysterious. Why? Because e is the real number, x is the real number, assuming that I have done my homework for real numbers before, so I don't have any problems with this part. This is just e to the power of x. This is the real exponential function. Okay? But this one is the complex exponential function. Okay? This we already know. We want to give meaning to complex exponential functions. But this is a very good way of giving it meaning, yes? Because we want to keep the rules of algebra the same. So this means that this is natural, but this one we learned today. What is that? E to the power of x. I copy and paste this part. And this one becomes cosine y by the Euler's formula. Yes? So if z is x plus iy, then e to power z is e to the power of the real part multiplied by cosine of the imaginary part plus I sine the imaginary part. Is it a good definition? How do you think how do you answer this question from a mathematical point of view? Because mathematics should be a consistent structure. Okay? So, what do you expect if y is 0? If your definition is a consistent definition, you expect that if the imaginary part is 0, the definition of the exponential function goes back to the definition of the definition of complex exponential function goes back to the definition of the real complex function. That is the meaning of consistency. So, do you think this meets your condition? Yes, because if y is 0, then cosine of y is 1, sine of y is 0, so this becomes 1, and e to the power of z matches with the normal exponential function. So that's a good definition. First of all, it respects the algebra. Do you remember? I didn't do it. I asked what to do. You told me this, so it was very natural. So you are respecting the old algebra, but we also have to check the consistency. Is the natural algebra that we learn in real numbers makes sense in the sense of complex numbers? We say yes, because if I put the complex part 0, I go back to the normal definition of the complex numbers. Anyway, so if you don't like these kinds of things, what you need to know for the exam is this. Okay? And now, can you tell me what is the absolute value of this complex number? If I ask you what, by the way, if you want to write it without writing x and y, can you tell me how should I write this? E to the power of z is e to the power of x. But what is x? What is x? The real part. So you can write e to the power of real part of z multiplied by cosine of y. But what is y? The imaginary part of z. So this is a little bit weird of writing the formula, but this is more advanced way of writing. So if I want to define e to power z, you see z on the left, and whatever you see on the right is just z. Okay, but this is a little, so e to the power of z, if you want to calculate e to power z, raise e to the power of real part of z, and write cosine of the imaginary part of z plus I sine of the imaginary. That's the same formula up there. Which one is easier for you to use? Okay. Let me ask you about these questions. Can you answer these questions? Let z be a complex number. I ask you 3 questions. What is the real part of e to power z? What is the imaginary part of e to power z? And finally, what is the absolute value of e to power z? So how can I answer them? So I told you, whenever you are supposed to answer these 3 questions, you have to switch back to the standard form. Yes? Okay, how can I switch back to the standard form? I would say, for example, let z be this complex number. Then e to power z becomes e to power x plus yi. Okay? But I don't want to repeat. If you repeat that part, you end up with the final formula. Yes? But this is not still a standard. You multiply e to the power of x in. So e to power z turns out to be e to power x cosine y plus I e to power x sine y. So this is your e to power z, and I hope that you agree this is in a standard form. So now if I ask you what is the real part of e to power z, what is your answer?
E to the x cosine y.
E to the power x cosine y. But if you want, it is not wrong to write it like this, but if you want to express everything in terms of z, not letters x and y, how can I write e to power x? What is x? X is the real part of z, and cosine of y, y is the imaginary part of z.
Babak,
Yes.
can you really call it the real part of z if the imaginary part is included?
Yes, yes, that's the whole point. If I write a complex number in the standard form, this number is always called the real part.
Even
And
if
that-
it contains some imaginary.
Yeah, it's exactly the same
Okay.
thing. Yeah, that's the whole point of defining real part and imaginary part. Because if I have a real number,
Mm?
the real part is the same number itself.
Mm.
But if you have a complex number, you have this freedom that you might have a real part and you might have an imaginary. Okay?
Mm.
And now here, what is the imaginary part of e to power z? The coefficient of I. So which is e to power x sine y, but if you want to express it in terms of z, e to the power of real part of z again, and then sine of imaginary part of z. So these are the formulas. But of course, the last question, what is the absolute value of e to power x? E to power z. What is the absolute value? But the absolute value has always one single formula. It is the square root of the real part squared plus the imaginary part squared. Yes? So what happens? What do I have? The absolute value of e to power z is the square root of the imaginary part. The real part is this part squared plus the imaginary part squared. But let us simplify, because this can be simplified a lot. So this becomes square root of this number to power 2 is e to power 2x, this number to power 2 is cosine squared y, and this number to power 2 is e to power 2x, and then I have sine squared y. What do you think I will do now? Factor e to power 2x. So what happens is becomes square root of e to power 2x, then I will have cosine y squared plus sine y squared, But this is famous. What's that? 1. So this becomes square root of e to power 2x. What's the answer? This means e to power 2x to power 1/2. So this becomes simply e to power x. So the absolute value of e to power z is e to power x. So if I want to write it, absolute value of z is e to the power of real part of z. Do you have the book with you? Can I borrow that? There was a national exam. Thank you. There is a national exam problem there in the book. Let me also solve that. You see that this is not hard at all. So, but of course, this is an old exam. It's better because older exams used to be harder everywhere in the world. Yes. Okay. So I mean, even this is supposed to be harder because it's from 1998, but it's still very simple. So. This problem is where? Yes, problem 5274. Problem 5274. This is on page 203. So show that 6 e to power I pi over 3 minus I pi over 3 divided by 3 e to the power of I pi over 3 is this number, minus 1 minus I square root of 3. Thank you. Okay. So this is the national exam problem. We want to show that this is equal to that number. So I don't think it's hard for you. You immediately realize that 6 and 3 can be cancelled. So because I want to prove an identity, let us just start from the left-hand side. Okay, 6 over 3 is 2. Okay, what do you think I will do here? Just follow your instincts, yes? For example, if I give you e to power 5 and I write e to power 2 here, what do you do?
E to the power of 5 minus 2.
5 minus 2. So you do the same thing here. So this becomes e to the power of minus I pi over 3 minus I pi over 3. Yes? That's the same idea of you write the base, you subtract the exponents. So I wrote the base, I subtract the one above minus the one below. But these two numbers are coincidentally the same. So I can write it as what? Minus 2I pi over 3. Minus I pi over 3, another minus I pi over 3, so it's minus 2I pi over 3. But can I use the Euler's formula here? Yes, if I just rewrite it a little bit differently. So I write 2, copy paste, e to the power of, instead of putting I here, I put a positive I here. Then what should I write here? It's minus 2 pi over 3. So the reason that I put it in that way, because I want to make this argument e to the power of ix equals to that. So I give the role of x to this. I copy and paste 2, and then it becomes cosine of minus 2 pi over 3 Euler's formula, plus I sine minus 2 pi over 3. But you know that cosine of negative, this negative sign disappears, and then this minus sign goes out. But this is 2 times pi over 3, 120. 120 is also a famous angle in your formula sheet. I have it in my memory, so let me just write them. Cosine of 2 pi over 3 is minus a half. Sine of 2 pi over 3 is a square root of 3 over 2, but I have a minus sign here. It's minus a square root of 3 over 2 times I. Yes? And then I multiply these 2 in. If I multiply 2 by minus a half, 2 and 2 are cancelled, minus 1 is left. If I multiply 2 here, 2 and 2 are cancelled, minus a square root of 3 is left, and there's another I here. And that's exactly the number that I want to reach the right-hand side, yes? Yeah, so that is also simple. And there is one example in the book. Let me also do that. So you want to, the example is this. Find a z, a complex number. So I'm not asking you find all of them. Find a complex number z such that e to power z becomes I. I don't know if people are waiting there. Okay, so we are not in hurry. So e to power z is equal to I. Okay, so how can I do that?
Maybe we can write it in standard form and then choose.
Okay, but so exactly as before. So I would say let z that I am looking for is equal to the standard form this, as you said. Yes? But of course, when I write it in the standard form, then I have two problems rather than one problem. I need to find x and b. Yes? And now, e to the power of z, as we learned, it becomes e to power x plus yi. So this means that now, if I put this into this equation, I would write e to power x plus yi is equal to I. Yes? But if this number is supposed to be equal to this number, do you agree with me? The absolute value of this number should also be equal to the absolute value of that number. It's always good. If you have two complex numbers, you want to force them to be equal. Of course, the absolute values should also match. This is a good idea because it gives you one equation immediately. But I don't know. Do you know that what is the absolute value of I? You can use the formula, but it's simpler than that. Where is I? I sitting 1 unit above the origin. What is the geometrical meaning of absolute value? Is the distance to the origin. So what's the absolute value of I? 1. If you don't like it, you need to write I as what? 0 plus 1i. And the square root of I is square root of the real part squared plus imaginary. You get 1 again. Yes? It doesn't matter. So this number is 1. But we just learned about that. Unfortunately, I erased that. You can see your notes. So what was the absolute value of e to the power of x plus yi? It's somewhere in your note. E to the power of x. So the absolute value of this one is e to the power of x. So this means that e to power x is supposed to be 1. But remember, x is real. So it means that momentarily you go to the world of real numbers. Yes? E to power x is 1. What is that x? 0. So no doubt about it. Okay? By the way, they are asking for a complex number. So you don't need to make a problem hard. You just need to find. You found x. What is the natural thing to do? Take this x, put it back here, then find y. Okay? So this becomes e to power yi. So if x is 0, then e to the power of yi becomes I. But this is exactly the Euler formula. This becomes cosine y plus I sine y is equal to I. Yes? But how can I continue? Because I just told you. What is I? I can be imagined as 0 plus 1i. So I in this form is a complex number. This is also a complex number. I demand to make them equal. This happens if and only if what happens?
Both.
The real parts match. So it should be 0. The imaginary parts also match. Yes? So then you need to ask a question. By the way, here the book has asked you to find a complex number. So you don't need to solve this in its full generality. Okay? So can you guess an angle whose cosine is 0 and its sine is 1? Because you want to find just one answer. 90 degrees. But because we are working in this exponential, so write it as pi over 2. Okay, so the problem is solved. Z is what? X is 0, y is pi over 2. This is your complex number. But let us try to make it a little bit better. If I ask you solve this equation, I do not mean find one answer, I mean find all of them. What do you answer in that case? Which part will change, do you think? So let us assume that instead of asking you find a solution, I ask you to solve the equation, because the word solve means find all. So solve e to power z equals to I. So you see that everything that I have done here is valid. Only here, I don't get one of them, I want to find all of them. Yes? So this means that you continue everything. You continue, x becomes 0. And then you can continue, you have your system again. But can you now tell me what is this general solution to this system? I don't want one y, I want to find all y's with these two properties. Cosine should be 0, sine should be 1. Where is it located? Cosine is related to the x coordinate and sine is related to the y coordinate. So you want to have your x coordinate 0, your y coordinate 1. Where is that? Where is that?
90 degrees.
90, here.
Yeah.
But in that case, you guessed one of them. Here, you have to write all of them. Can you tell me what is the formula that gives all of them to me?
Pi over 2 plus n2 pi.
Yes, n2 pi or 2n pi. Yes, exactly. So y becomes pi over 2, but not this one. I can go one full round in this direction, 2 full rounds, or the other way around. So you remember from trigonometry, we have to add this, and then we put n belongs to z. Okay, so now if you want to solve this equation, so how should you answer the question? The question is that z is equal to, x is already 0, but y is not one answer. There are infinitely many answers for that. Yes? So what's the answer? It's pi over 2 plus 2n pi multiplied by I, n belongs to z. That is also weird, isn't it? Compared to real exponential functions. Why this is weird? How many answers I got? Infinitely many. This is not what you expect. Yes, because if you have an exponential function, e to power x is this one. If the number is 0 or negative, I do not have any solutions, but if it is above that, I have exactly one solution. So if I give you e to power of x to equal to 5, what is the answer? Do you remember? Only one, ln of 5. But here, this is an exponential function, but in the realm of complex numbers, and this is just one constant. But how many answers I got? Infinitely many. So these weird things can happen when you are working in the complex numbers. Any questions? Okay, so this chapter is completely finished. Let me stop recording.